see much further than we should. You're sick of the lies, sick of the lies. Who you gonna call when you get on the line? Who you gonna call? Who you gonna call? Who you gonna call? Yeah! GLOBEBUSTERS! 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 If there ain't no curve, there ain't no ball. The globe religion about to fall. We're gonna open your eyes so you can see who you gonna call if you wanna be free. GLOBEBUSTERS! 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 Who you gonna call? Who you gonna call? Who you gonna call? Yeah! GLOBEBUSTERS! GLOBEBUSTERS! GLOBEBUSTERS!
And welcome everybody to GLOBEBUSTERS. We accept the reality of the world with which we're presented. It's as simple as that.
Hello, everybody, and welcome to another edition of GLOBEBUSTERS Tech. I am your host, Zach. Good times for all. And today we will be discussing the downward vector. This is a topic that kind of hits home with me. I've done a lot of research on this topic, a lot of testing, a lot of, just really hours and hours and hours of just thinking about this and how it was caused. And my ideas have changed over the years. I remember just hearing a Mark Sargent reading an email that I had wrote to him back in like 2016. And I was thinking that maybe it was 2015 even. It was early on. Whenever he had started the show, it was pretty early. And I had the idea that, if you take a gyroscope that's spinning in one direction and you take the casing and start spinning in the opposite direction, it inverts itself and starts rising up. And I don't know, I saw a force being created there, that was kind of a representative of our downward vector that we see here on Earth. And yeah, so that's just one of my very, very early ideas on how this all works. And of course, I have thrown that one out the window like you do when you learn about new things and new types of physics and all these other phenomena that will negate that. And that's how I've come to the conclusion the downward vector is created by the electrostatic field that we have, or the electric field, if you'd rather just call it that. But before we get into all of that, we're going to say hello to the panel. Starting off, we're going to say hello to Mrs. Cami Nodell. Cami, how are you doing today, ma'am?
Oh, I am doing really good. I'm glad to be here. It's good to bring some clarity to this topic that's been on the table for so long, and it's so clear in my mind. And then people hit you with chat questions, and they want you to give the whole explanation in a 33 character or whatever your limit is. How many words to do it? It doesn't quite work out well that way. We've covered it on a lot of shows. For those that don't know me, my name is Cami, also Aisling717 in the chat. Bob of GLOBEBUSTERS was my husband, and the tech show is not the Primetime Sunday show. This is a passion project of my husband's. It's pretty much a nerdy drill down tech talk. And so I want to welcome everybody to the show tonight. If it's not what you're expecting, that's fine. It's not going to be for everybody. If it is, welcome. If not, please join us on Sunday for our big primetime show. And for those that are here tonight, thank you again for joining us. And I'm going to throw it back to Zach.
All right. And next up, we have Miss Karen B. Karen, how are you doing this evening, ma'am?
Fantastic. Great to be here.
Excellent. I know I know you have been getting all kinds of emails and messages about this very topic, and
Yes.
it it was time. I mean, I have beaten this topic like a dead horse. If you go to my channel, I've been doing videos on this topic for years and different demonstrations and, just observations that explain what I'm talking about. And it's just hard to keep talking about something. I have trouble doing that. I do.
Yeah. Yeah. I feel like this subject was settled for me, in my opinion, right? So I was kind of surprised to see it start coming up again. But, maybe certain people were busy doing other stuff when we were having this conversation. And so we need to revisit it. They want that's being challenged again. And I don't want to just blow off our peers, you
No,
know?
exactly. That's why it needs to be addressed. I'm glad you brought this, forward because it really does. I've been putting it off because I just am sick of talking about it. But yeah, you're right. People have questions, they want answers, and we need to at least give them our idea of how this is all created.
Right.
Yeah. So thank you, Karen, for making me do this one.
No, thank you.
And next up, we have Skylar from the Troubling Tribune channel. Skylar, how are we doing this evening, sir?
I'm doing fantastic. Thanks for having me once again. I think that this topic is it's very interesting that it comes up and it causes so much division in the community, right? Or so much controversy. I think it's hilarious, right? One thing that we can definitely all agree on is that this right here does not mean that Earth is a ball with a radius of 3,959 miles, and that it certainly doesn't have anything to do with the way that things move in the sky, or does it, right? Tend to have an open mind when it comes to introducing the electrical field theory and how that plays into the lights in the sky. So I'm interested to hear all the thoughts.
And yeah, I'm glad you said that. This doesn't change much in our model. This is one factor in our model. And it doesn't change the shape. It doesn't change any of our main basic points that we want to get out to the public. So yeah, I would like to try to eventually open up a Discord with some of these people where we can actually have rational, calm, non-emotional conversations. That's how it needs to be approached. When you're speaking about physics, emotions, and, well, I like this person better than this person, should not be in your mind anywhere at all. You should be turn on your logic part of your brain, and that's what should be driving your ideas from that point forward on that topic. It shouldn't be about this camp or this camp and this and that, and that's silly. That's infighting that we don't need. We already have a big enough uphill battle fighting mainstream science. We don't need to be fighting each other. So yes, we can
What
disagree.
what matters is what is said, not who said it.
Exactly. So, having said that, we'll come to our last and final panel member here, Mr. Kyle Adams from the Kyle Adams channel.
Yep.
How are we doing this evening, sir?
Happy to be here as always. Just celebrating my victory and finally getting rid of that whole, or getting the Journal of College Science Teaching to retire their article that claims science never proves anything. After I made a big stink about it for the past year, fighting that article, just saying, you realize that if you say that, you can't even claim that some cats eat food. And yeah, it's just been crazy. Just the kind of
Well, that's
mess
awesome.
that's
So how much of a back and forth did it take? I mean, how many messages did you have?
I just sent one email out there and I attached like some videos to it that I've done, but I've been continually making videos ever since then, bringing that up like all the time. And yeah, I think it was kind of a weird little miracle when I finally just decided, you know what, whatever, I'm just going to burn this thing. And I just kind of felt like prompted to do so. Just burn the article like an actual copy of it in my driveway, basically, and just set the thing on fire. And then all of a sudden, like
after doing that, and so I'm like, go back to the inferno from whence you came. After I did that, all of a sudden I got online, and all of a sudden it's not there anymore. I'm like, what? That is so weird.
Wow, that's
It's so
wild.
weird. Like, yeah, the moment I did that, it's gone. It's so crazy.
That is awesome, man. Well, congratulations. That is an
Thank you.
awesome achievement. Changing a scientific journal is no small feat, really. You need, you have to be heard at least by that scientific journal.
Yeah.
So you know that they at least heard you,
Yeah,
or
it's got a
somebody
lot of other
heard you
articles to help
and
out, though.
heard you mention that. And yeah, great job, man. Awesome.
Yeah, so that was the kingpin. Now I've got to go get the smaller ones that kind of follow after that, like National Geographic, Scientific American, and all these other people repeating the same garbage.
Well, keep on it, man.
Okay.
We'll get them all changed eventually.
Yeah.
All right. So the downward vector. What are some ideas that you guys thought it might have been in the early goings? Or even right now, you may have a different idea on how it all really works. Before we get into some of the things I'd like to present.
Well, I know Eric Dubay. He always points out, it's always just a matter of buoyancy and density, and those are his two favorite words. And he really gets those words from parallax, from the whole
Robotham.
Yeah, Robotham, Samuel Robotham. That's who he gets it from, and he just quotes from there. And there's parts of that I agree with, and parts of it I disagree with. And I don't think density by itself is a force. It's a contributing factor, but things have like density for a reason. Things have buoyancy for a reason. And so you're just kind of taking the cause. Sorry, you're taking the effect and treating it as the cause. And so I think that's my take on it.
Were you going to say something, Karen?
No, just that, in the beginning, I really didn't know what it was, but I know that a lot of people were talking about density and buoyancy, and that seemed to be enough early on, but then you get into like some of the minutia of how things work in this realm, and you realize that density and buoyancy really just isn't quite enough. It's like the density and the buoyancy need to know which direction to distribute their density and buoyancy, if that makes sense. Like, it needs to know where to find its equilibrium, right? Because density and buoyancy have to find their place somewhere. There's a density and a buoyancy because there is an up and down, and because there is, a difference. So you start to figure out, after thinking about it for quite a while, it's not quite enough. And then I remember watching Ken Wheeler early on, and he talked about gravity being basically kind of not in such an easy way to understand as like the way you talk about it. I know he always talks about, well, if you can't explain it to a child, I'm like, bro,
Then
I have a
explain it
hard
to a
time.
child, Ken. Yeah, I know.
Yeah.
That always drove me nuts. I subscribed and unsubscribed from Ken Wheeler like 4 times before I actually decided to learn what the words meant that he was saying. Because he would say things like that. Oh, if you can't describe it to a child, then you don't understand it. And then he would go off.
And I was like, well, I'm not getting it. Am I a complete retard, or what's going on here?
What if it's legitimately word salad sometimes?
Yeah, you do need to. He uses words that he's just so familiar with them. I don't think he even realizes, like, most people don't know some of those words.
Yeah.
But
You use 2 words back to back that are mean the opposite of each other to describe the same thing. I don't know what to make of that.
But once I just kept at it for a while, and I was like looking up words, and I downloaded his PDFs, and I started to get a basic understanding of it. But once you started doing your videos and you guys were really breaking it down, then I was like, yeah, I get it now. And it all started to make sense, and I was pretty comfortable with that conclusion. I still am. So
I'm actually I am a fan of Ken Wheeler, just so everybody knows. But one of the things that to also answer the question, throw my hat in the ring, I was also in the camp of like, oh, it's just density and buoyancy. But to be honest, it really was the same kind of issue. It was a failure of understanding, right? It was kind of just assigning the effect as the cause and just running with it, right? But um, yeah, one thing that I did know is that it couldn't be the Earth accelerating upwards, because if it was a consistent acceleration in that regard, then the gravity 9.8 meters would actually be a constant. It would not be an average that is assumed to be constant for the math. So with that being said, it means that it's not just one thing. It has to be all these different things with their different relationships, with then again a downward bias being set, which I think is funny. I didn't come to the conclusion that it was electricity all at once, like you guys kind of brought to the table. But I did have the thought way back when, like 2015, I believe, when my friend was talking to me. He's like, "Well, what about the tides? Right? If it's not gravity, then what's causing the tides?" And this led me down this rabbit hole where I'm like, well, what is causing the tides? And I saw this experiment where somebody took a balloon and they rubbed it on their head. They put it next to a stream of water coming down, and they were actually able to pull the stream towards it. And I was like, what? So maybe the moon is giving off static electricity, which is causing the pull. I mean, after all, it is agitating people on full moons and yada yada. And you kind of weave through the deceptions one by one, right? But it's pretty funny how close you can get, because once you realize that, oh well, things are affected by static electricity, and they're also not just the whole idea that they're just attracted or they're just repulsed. Somebody, a Glober, tried to say that in one of the debates. It's just absolutely untrue. You can stick it to your head. You can also it was actually pushing the water, I believe. I'll have to go back and look at the experiment now. Maybe I misremembered.
Well, yeah, it would be determined on whether it was higher potential than the water or lower potential than the water. If it's lower potential, then it'll draw the balloon towards it. But if you have a higher potential, it'll push the water away a little bit.
Gotcha. Yeah, I'm gonna have to go back and look. It's been years.
Yeah, most likely, most balloons, they hold, like when you rub them on your head, the balloon, since it's rubber or plastic type, it will hold the lower potential and you will get the higher potential. And then that high potential is going to probably go through you down into the ground and try to find the ground. But you're putting a lower potential. That's why when you stick it to the wall, it can just stick there.
Yeah, makes sense.
No, maybe it would be a high potential then. I don't know. I'm not sure. I'd have to think about it. Yeah, and it's not always definitive. I've shown that you can polarize a balloon. So one side will be positive and the other would be negative or lower potential. Yeah, it's amazing how things insulators actually hold the charge more. Like a conductor, the charge just runs right around it. Boom, runs right across the surface into the next object it's touching. While an insulator is going to hold onto that charge for a while. I had a balloon polarized for over a week and a half, to where I could go and rub my little stick that I used to charge it up, and I'd put it near the balloon, and the balloon would spin around until the poles were lined up again. Yeah. So electrostatics is really amazing. If you'd like to learn more just about electrostatics, I know a lot of my videos, I need to remake them. They're really grainy and it's like 480p, but I don't know how many, probably 20, 30 videos on electrostatics alone and showing different phenomena taking place when you apply it in certain ways. And these things happen in nature. It's not like I'm rubbing this and then an electric field is created between us, between me and the lighter here. They're already right now, without me even touching it, we are exchanging electricity, this lighter and myself. Not very much. Your right hand and your left hand have a very weak potential difference, but there is a potential difference here. So just this little bit here, there's electricity flowing between my finger and this lighter all the time. I know we can't see it, we can't do, but electricity is scalable. And when you start ramping up that electricity, if this was, about 5,000 volts, then I would get a discharge and you would see the shock. Kind of like when you touch a handle of a doorknob and get shocked, or touch another person, rub your feet on the carpet and go touch one of your friends and they get that shock. A quarter inch is about 5,000 to 10,000 volts of electricity, depending on the atmosphere, how humid it is, things like that. The lower the humidity, the easier it is for the electrical breakdown of the field to occur, because water is an insulator. Okay, we're getting off topic. I'm sorry. I can talk about electricity for hours and hours and hours. I love it. I love electrostatics. Okay, Cami, what about you? At the very beginning, did you think that it could work with just density and buoyancy, or were you always under the impression that, well, okay, it's not mass attracting mass, but there must be something?
I always knew there. I don't know if no is the right reason, but I've always been on the track that I understand buoyancy density well, and I had on my desk for over 30 years a set of something called specific gravity liquids that I actually used it in a day-to-day test. Testing on it's one of the properties of minerals is the density of them, and we would test it with with liquids. And so I was very, very familiar with it and how it worked. I was also familiar with chemistry and how, again, you can change the dynamics of things by mixing them together. I never thought it was just buoyancy density. I mean, one of the things I get most, I don't know if confused is the right word, but most, I guess I don't get it is that people, when I listen to them talk and I listen to the debates and the arguments, everybody takes one little element and breaks it down and puts it into something very, very unrealistic. It's just not in flat earth. This is like in science themselves. I've watched video after video on monopoles, for instance. We'll get off topic here. But with the monopoles, they were trying to find the attractive only and trying to cut down a system that you couldn't cut down a system. You can't cut down a magnetic system and have just a part of it. It's part of a system. And that's what I think that we're doing is that we try to isolate little parts out of a system when things always work together and they work in reality, in the way the world works. It's a very, very dynamic system. And so if you, again, overcomplicate by isolating things, and I call it complicating it by isolating them because in reality, they're not isolated. I think you'll run into problems. So calling it one thing, I thought early on, I thought it was a combination of, because I'd studied even before going into that monopoles a lot. It was a nerd passion of mine. And so the way that they were trying to break up monopoles, again, you already have the nerdy passion. I always thought incoherent magnetism, and the way that if you take magnetism, what you think of as ferrous magnetism, and make it incoherent, it's attractive only. So if you think of the things falling here and making an incoherent base, you've got a base of it. You measure the volts per meter. In other words, as these pieces started to click in realities, the system started building it. You'd pick out pieces of the system that were there in reality that are working in reality, and you see them. In other words, you're not making anything up, and they're just there. So to me, it's like people are overcomplicating this by, again, we know the volts per meter there. We know the effect it has. We know the incoherent magnetism is there. We know the effects it has. We know the buoyancy and the density is there. And then we know the effects they have. And when you start putting the whole system together, it's working. And as soon as you start trying to isolate and say it has to be this one thing, I think we're going to run into problems. It's not one thing. So that's my take on it.
All right. Yeah, I'm kind of in the same boat. It never sat well with me that it was just density and buoyancy. That explains so much of it, but there has to be a direction, something that tells dense, this is the way you're supposed to go. And then the lighter objects, they're not told so much to go up. All right. A lighter object isn't trying to get up, it's being displaced up. Things only accelerate in one direction, naturally, just one direction. When you release your helium balloon, it does not accelerate and keep accelerating until it goes up and explodes or pops. It's a very slow rise. It actually slows down as it's getting closer to its equilibrium.
Equilibrium, yes.
It doesn't accelerate. There is only one direction that things accelerate, and that is down. And denser things accelerate down. Now I know that's a big thing in um, what Dell is saying, that things aren't accelerating, and measuring acceleration is extremely difficult to do by eye, looking at it with your eye, or even with a camera phone that is 400 something frames per second. It's and dropping it from maybe only 10, 20, 30 feet. It's hard to do without really precise instruments that can measure down to the thousandth of a second. And that's what we're going to show you here. But just a thought experiment. We need to understand what accelerating means. So accelerating means that if I drop something from the bottom of this ruler right here, the speed that it's traveling when it passes through these two will be at a certain speed. If I then raise it up higher, and the speed that it is traveling when it passes through these two is higher, that means that it accelerated. It is picking up more speed the further it falls. Okay? So that's what acceleration means. It means that it's going to keep getting faster and faster and faster until its potential is stopped by something. Now, any of us can go try this at a pool. You can jump off the edge of the pool into the water and feel the water hit your feet. Then you can go jump up on a high dive and jump off the water and feel that water hit your feet. It's going to be at a higher force. You're going to feel it. So you can test this at home. That's why they say these people who jump from, like the cliff divers that jump from 100 feet, when you do that, you have to know how to hit the water correctly, or you could kill yourself. People
Yeah,
die
that's
jumping from 100 feet.
well, that's how people do that on purpose from the Golden Gate Bridge all the time.
Yeah, it's now people don't jump off a 5-foot thing to commit suicide in water because it wouldn't work. You would belly flop. It might sting a little, but you're not going to kill yourself. That's an acceleration right there. When you drop something from a higher distance and the force that it exerts when it hits another surface will be higher if it accelerated. Now, if there were no acceleration, then you could jump off that bridge and it would feel like you were hitting the water just jumping off the edge of the pool. There would be no difference. You'd be falling at the same rate. Is this making sense to you guys?
Yes.
Oh yeah, makes perfect sense.
Okay. So when we bring acceleration in now, why does acceleration matter so much? If the Earth were accelerating up, it would mean that it would have to keep increasing its speed. It wouldn't be a constant. So when you drop something, the next time you pick it up and drop it, it would fall faster because the Earth would be accelerating faster. This does not happen. There is no, eventually things would, I don't even know if you could pick them up off the ground if the Earth kept accelerating up, because the G's would keep increasing. That G force, we call it, right? The gravitational force. I know, I don't like the word either, but we're going to use physics terms. So the G force exerted on your body would keep getting higher if the Earth were accelerating up. And this is not the case.
G-force just means acceleration. And so
That's
they're kind of
it.
the same thing.
Yes.
So
Well, and they also like to say to me that the Earth isn't accelerating, it's moving at a constant speed.
Well, we're going to show them here in this little video. I want one of these little digital timers. These things are amazing. Let's see, who is it that did this experiment? A-level physics, HQ. Very interesting. He has a lot of neat toys that I want. Neat channel. Go check that out. A-level physics, HQ. So I'm just going to play a little bit of this. He's going to show you, he's going to drop it from here, and then he's going to keep going up 10 centimeters, and we're going to see the speed, the amount of time that it takes to fall through here. That's what he's measuring. The amount of time it takes for this piece of metal he has attached to this card to actually fall through those two cylinders there is going to increase, or the time is going to decrease, meaning that it's falling faster. So here you go. Here's acceleration.
Square and plot on our graph. So here we go. 0.037. Okay,
I want one
let's
of these. They're
repeat that.
so
Reset
accurate.
the timer.
That's
And again,
fascinating.
Wish his hand wasn't blocking it so we could see exactly where it was.
0.037.
He says he has it right at the very bottom of the
Now
ruler.
we're
He's
going
putting
to
that card up
20
right to the
centimeters.
edge
So
of the
that's
bottom of the
10
ruler.
centimeters on my ruler.
But just think of that accuracy right there. He dropped it 2 times, and this down here is 1,000th of a second. So you have your 10th, your 100th of a second, and your 1,000th of a second. That
Wow.
measured 1,000th of a second, the exact same 2 different times. It said 0.037 and 0.037 both times when he dropped it from that height. That's very precise. I want one of these to play
Yeah.
with.
Interesting.
Okay, you're now going up to 30 centimeters. So 30 centimeters, sorry, not 30, we're going up to 40 centimeters. So that's here. Then we'll do 50 and then 60 at the top. I'll be dropping from out of the view range of the camera. I'm keeping the camera focused down here so that you can see the timer, since that's the measurement we're taking. So this is 40 centimeters.
So do you see what he's doing here, folks? He's showing that this
Yeah,
little thing he's dropping, it's moving faster through here. The
Yeah,
time
the
keeps
higher
going down.
the higher he drops it from, the faster it drops.
Which means it's accelerating.
That's
The claim to fame that I keep hearing about, though, is if you do this during a thunderstorm, it'll drop at a different rate.
Now you
Yeah.
definitely need to get one, Zach.
I know. I know. There's so many tests I want to do with
I'm
this thing.
interested. Yeah, that'd be a fun toy.
One of these
There was
days.
Whitsit over there. He was talking about that, about how if you do this in a thunderstorm, it'll drop at a different rate. And they've done this at like the big labs, with like in a vacuum chamber, like underground and all this other stuff. And they're like, what's going on? And they've got like whole scholarly articles talking about it, and they can observe it happening, but they don't know why it's happening.
Well, yeah, just to get off topic a hair, but like in a thunderstorm, the electrostatic potential between the ground and the clouds, say there's a really high potential above the cloud. Well, the bottom of that cloud is going to then be a lower potential, maybe even than the Earth. And when that happens through induction, that low potential right here is going to pull all the high potential that is in the Earth to that one spot. And you get a reverse. And that's how we get things called updrafts. People who go, what is that called when you're on that hang gliding or paragliding and all that kind of stuff? When you do that, you have to be very wary of thunderstorms because you will get these updrafts, and sometimes they can throw you 20, 30,000 feet up into the air, just straight up in a vertical shaft. The air is actually rising upwards because of the potential difference from the ground to the, it's amazing. So let's let him finish this out here.
So that one skimmed the light beam, it didn't fall properly through it. Okay, so that's all the data collected now, and in the next video I'll show you the
Okay. But yeah, that's, and I mean, if you just think about it, folks, you're just do the thought experiment in your, or not even in your head. Find a pool, drop something from very short off the water, just right above the water, drop something, bloop, and then drop the same thing from much higher and just watch the splash. That will show you the difference in the force of it hitting that water. That means that there is an acceleration there. If the Earth were the thing accelerating, then the next time you dropped it, it would fall faster. I don't know how to explain that anymore
Oh, I
beyond
think you
belief.
explained it really nicely.
Yeah, no,
I
he
just think
keeps on
about
saying you need to address your stationary claim here. If the Earth were moving and accelerating, then it would fall faster the next time you dropped it, and faster the next time you dropped it. In fact, because it would have to keep accelerating.
Yeah, I think the claim is that you're moving along with the Earth, and so because you're bringing it up to a faster rate, and so it's kind of canceling each other out. I think that's the claim that they're going with. It's still totally just ridiculousness, though.
Yeah, but that's the thing. When you drop it one time, it would move, he would drop it on the thing and it would read 0.017 or whatever. But he could drop it from the same rate. And if the Earth is accelerating, it would then fall faster from that same rate.
Yeah.
It wouldn't fall at the same time he was getting there.
The really funny thing about this whole Earth accelerating thing is these are like the globers that are saying this. This really comes from Albert Einstein and his whole theory of relativity. That's his
And then they
claim to
say,
fame.
but they're in their chat saying not claiming acceleration. Well, how do you explain the different rates of fall from different heights? That doesn't make sense. If the Earth is moving up at a constant speed, then as soon as you let go of something, it's dropping like it's hot, like right from the get-go at that speed. So it just doesn't make sense to me.
Yeah, there has to be an
especially
acceleration.
Especially if you drop two different objects at the same time at different heights, and all of a sudden, this one's going at a different rate than this one. That doesn't work.
Yeah, it's apparent that there is an acceleration.
Oh, so they say, when you drop the object, it gradually loses upward velocity. You know what? Then if that's your argument, then why are we even having this conversation? You guys just want to believe whatever you want to believe, and you're going to make up whatever excuse you can to push your idea that the Earth is moving upward. And then what are we going to do? We're just going to agree to disagree. How do you prove either way what's going on?
Let go of the Flat Earth Society, okay? It's garbage. They're just repeating Einstein, and Einstein over there is, that whole claim doesn't work on a ball anyway, because the ball will get ripped apart.
What clicked in for me, and we haven't gotten into it yet because he's like pretty much defending against it instead of saying how it works. But what really clicked in, like a lot of the pieces for me, was the right-hand rule and no work required. When they started doing the no work required along this axis, that things can travel on this axis with no work required, and you put in the model and dropped it, and they in physics demonstrated on a sideways. Again, if you flip the arrows up and down and model what we are with our electric field, all of a sudden the answers, the no work required to move along this axis, and you put in the buoyancy density along with it with the incoherent at the bottom, it clicked in. So what I want to know is, these things are there, we measure them, they're there, we can test them, we can repeat it, we can do all of the tests on the pieces together. And why would we need to create something moving up? In other words, I think you're creating so many problems and issues with looking for something that's not there when the movements that we're sensing, I see the answer. So in other words, it's like if the answers are all there in nature and you can sit there and look at the observable nature that, again, on the right-hand rule, no work is required to move on this axis, and put it into it, that answers your question of your acceleration and why there's no work required. I don't know what they're looking for with moving it up.
Well, I know one of Dell's contentions with the electrostatic side of things is he's quoting the ideal gas laws, which are not real.
Right.
They state this. Any physics professor, when they're teaching you about ideal gases, will tell you that an ideal gas is not real. It has no intermolecular forces. It's assumed that there's no intermolecular forces on these gases, even though any gases within an electric field will have intermolecular forces. So you're removing the electric field just right off. And then you're
Taking it out of reality.
I'll let this gentleman explain it here. Yeah, and this is one of those things you can go check out on my channel, is me playing with all these different types of matter. I'll show you here that I can bend water using electrostatics. I can make water that is just smooth. The surface is not moving whatsoever, but the surface is bent like this. Okay, I've done this. Dell knows this. He's shown this on his show before.
You can bend water. You can change the weight of an object. It just goes on and on. Like there's
electrostatics. Yeah, it affects gases.
Evidence of this.
Gases, when they become so highly electrostatic charged, they ionize and become a plasma. That is affecting the gases. The gases are actually on my Van de Graaff generator, which Austin has right now. If you put a nail on it and crank it up, you can feel the wind coming off that nail and blowing on your hand. I have a video, I'll have to find it, but of me blowing on a candle doing this. And it's really hard to test these things though, because you can't see the gas. So I've done it with smoke. But then again, people say, oh, well, it's the particles of smoke that are taking the charge, not the actual gases. This is something that you can't see. But ideal gases are a mathematical system to make the way gas behaves easy to predict mathematically. That's it. It does away with any electrostatic potential differences, temperature variations from like up here to down here in your container. No, it's all the same temperature. It's all the same amount of pressure. But now this is why we have a pressure gradient here on Earth. If the ideal gas laws were real, we would not have a pressure gradient. They would fill the available space, right? Like everybody says, oh, the gases fill the available space. Well, no, yes, they've filled the available space, but they haven't equalized. They never equalize. There is high pressure down near the bottom of, near the surface. And the higher you get into the air, the pressure becomes less and less. It is not equalizing. So it doesn't matter where you put the gas in either. Sodium hexafluoride will sit in a container in a tub and you can actually float things on it like a boat. It's a gas. It is not just spilling out and filling the available volume. So ideal gas laws state these things, but it's not how it works in reality. They've removed reality from their ideal space to say what the gases are going to do. But this has nothing to do with how it works here on Earth. Okay, we're going to play this video here. Okay. This is Quantum Brain Tutoring. He's only got 49 subscribers, but he's pretty smart. I've been looking through a couple of his stuffs, and yeah, not a bad little channel.
Okay, super quick video, no messing around. Ideal gases, you know what they are. They're gases that don't have any external forces acting upon them. Everything's elastic, all the collisions are elastic. There's no loss of kinetic energy. You know this, you're doing A-level physics. If you don't know this, learn it, right? But ideal gas assumptions, you need to know them. 3 or 4 marks in your exam, easy marks. Check out the tutorial video and I'll explain what these assumptions are.
Okay, let's try and discuss this question. Shorter video, much simpler than our previous video on derivations, but this question says that we need to state the assumptions that are associated when discussing the behavior of an ideal gas. Okay, usually in exams it will kind of ask you for 3 assumptions of the kinetic model of ideal gases, but I'm going to give you 5. And, you know, just pick and choose whichever ones you wish, but let's just crack on. So we know that ideal gases are not the same as gases. Okay, we're dealing with a closed system in which no external forces are acting the same way that we are dealing with momentum, right, in a closed system. But the first thing that we can say is that the particle movement is random. Okay, so random motion. Okay, easy peasy. 2 is that obviously collisions are going to be elastic in nature, right? So no kinetic energy is going to be lost in that collision. Okay. Another thing that we can say is that no intermolecular forces are acting. Yeah, which makes sense. If there were intermolecular forces, then obviously we'd be having some of that kinetic energy lost, but that is not the case. Another thing that we can talk about is that the collision time is negligible. Okay, the collision time is negligible, and that is something that we need to assume because we know that the force is equal to the change in momentum over time. And obviously, if we're dealing with a system in which momentum is conserved and kinetic energy is conserved, then we can't really have a significant collision time, right? So the time of the collision itself is negligible. And finally, we can say that the volume of the atom is negligible compared to the volume of the container. Okay, so the volume of the atom is negligible when compared to the volume of the container. Okay, and obviously that is 1, 2, 3, 4, 5 points.
Okay. So there you go. You heard him at the beginning. There's no external forces affecting this place. There's no intermolecular forces acting upon each other. This is what happens when I fire up my Van de Graaff generator. Let me turn this back on. Oh, I'm over in the wrong spot. Okay, so when I crank up my Van de Graaff generator and I've got the say it's this right here, and I put a little nail on it, sticking out, right? The gases, now this is how they explain it. They say you have your proton and your electrons going around. We'll just use a helium. 1 proton, 1 electron, right? Let me move over here. So you have your 1 electron. Now, if the electric field is higher over here than it is here, then that flow will be this way. This electron is going to spend most of its time over here, actually. And the proton and neutron will be over on this side. Now, this is how they claim it works when you have one inside of an electric field. That 802, Electricity and Magnetism, Lecture 1, Walter Lewin. I'll actually bring up, this is his 801 course right here, where he's talking about fluid mechanics, gases and waters, hydrostatics, things like that. And he clearly says here at the beginning, I usually don't play too much of his videos because I've gotten struck plenty of times. So I'm going to try to keep it under a minute. I think it's like 1:05, but he'll say it twice. Once you remove gravity, he's talking about Pascal's law, which is one of the ideal gas laws. So right off the bat, now why he says gravity here is because this is 801. 802, he starts talking about electricity and magnetism, and he actually teaches them that it's electricity that is holding us to the earth and not gravity. So, but he says that it's very similar to gravity in so many different ways. It's a great course. I've done plenty of videos on these lectures, 802 electricity and magnetism on my channel. I call it Nothing But the Gravy. I take out all of the equations that he writes down and all that stuff, unless he's saying something very important while he's writing it down. And I just put in the parts where he says, you know, how the phenomena works. It's called Nothing But the Gravy. It's on my channel. Go check it out. But yeah, listen to what he says right here.
With a fluid, could be either a gas or it could be a liquid.
It could be. Did you hear that? If for now we forget gravity.
Yeah.
If for now
Forget
we
gravity.
forget gravity, and if we make everything elastic kinetically so it does not lose energy when it bounces off each other, and if you make everything as perfectly small spherical ball at the exact same time, and if you put all of these conditions into it, we can call it an ideal gas law and say that in other words, they create everything that does not happen in nature and call it
Yes.
an okay.
This
Just
is
making sure I'm
Narnia.
following it.
We're
This
talking
is yeah.
about Narnia.
So you take it out of reality to
Now,
okay.
ideal gas laws, they have their place.
Absolutely, in
They
engineering they would.
when you're talking about very low density gases, helium, hydrogen, things like that,
Oxygen works well with.
the answers that they come up with to do the math, and they still don't know because they've never really been able to test it. Even the gases I have, they say 99.9%, you know, because they can't. They don't know what's fully in there because gas is such a fluid dynamic system. It's hard to control. But and then as he goes on, he'll say it again. Go ahead, Kyle.
Okay. Earth does not have to be accelerating upward in order for gravity to be a fictitious force. That's not the only option. There
Yes,
are other
exactly.
options, and that's what we're diving into here.
Yes. And I'm not even really going to get into the electrostatics so much this part. I'm just trying to dispel some of the reasons why I claim it that there needs to be. Now, it could be something besides electrostatics. But right now, the only answer I see is that there is some kind of force being created, and electric fields create a vector. They do. I've done test after test after test, making material matter. I've done hair, I've done iron filings, I've done wood, I've done paper, I've done styrofoam, little pieces of plastic, and I reverse the electric field in between two plates, and I get them to fly up to the top plate and stick like that's the ground. So I've recreated all this stuff that I'm claiming happens. And I don't know how to say it any other way than showing you what I'm talking about. And then I know some of the words are big words and this and that, but you can see it. You can see it happening. So yes, an electric field does create a vector. An electric field does move matter. It just does.
It definitely creates a
It does.
vector. Try putting an electric field and then walking by it with a compass, and you'll see that it creates a vector.
Yes.
It creates a vector, and it creates a vector where, again, no energy is required to move along one axis. Things that would be that when we measure volts per meter going up and that, it's like, oh, there's, wow, isn't that nice that it's there and they can explain it. And like the good professor explains on the screen, he'll take you a little bit further later on, what they call gravity isn't needed until you get to outer space because the electric field and all of the forces that are already present on the local level account for everything here. They'll flat out say to us, we have everything we have here, but when we go into outer space and doing the orbits and the orbital mechanics of everything, we need gravity.
Yes. Level Earth says it beautifully here. Gravity only exists to explain the heliocentric
Yes.
model. That's it.
That's
it's
it.
not explaining things here on Earth.
Period.
Okay.
We don't need it to.
Those giant magnets that they use in junkyards to pick up cars and stuff, those require an electric charge. Do they not? They can be turned
Yeah, they're
on and off.
electromagnets.
Yeah,
Electromagnets.
those are the most powerful magnets that I'm aware of. And yeah, in order to get those to work, you have to have that electric charge. It's not just something like a magnetic.
Oh, that'd be
fridge
horrible.
magnet.
No, you couldn't let go of anything then.
Yeah, that's how they work.
You could pick it up and just hold it. Yep. Go ahead, Zach.
Okay, Glenn, thank you. Pressure gradient creates a vector too. Yes, it does.
Yes.
Okay, so here we go. Well, he's going to say it one more time about just removing in the absence of gravity.
The pressure is everywhere in this vessel the same.
Okay, now this does not happen. What happens to water the deeper you go? There's more pressure. Once you remove the downward vector, all the water would be the same pressure. That's what he just said. This is Pascal's law. These are the ideal gas laws. In nature, this does not hold to be true. Because in nature, there is no place where the downward vector is not present. That's just how it works. Even with gases, same thing.
Okay, so you got the closed container here, and you put the downward vector onto it.
No. He put a force on the plunger right here to
That's what I'm trying
compress
to
it.
say.
Yeah.
That's what I meant to say. So he's putting the force on there, and once you do that, the pressure is the same all along the wall of that container. And so you're comparing that to water in a lake. You're kind of putting a downward
Yeah.
force on the top surface of that lake. And
No. You don't have to
it's
even
not the
put
same.
you don't even have to put a force on it. The pressure, even without this force right here, the pressure is the same in this container without gravity. Once you exclude
Which is different
gravity,
than the lake.
now even gases inside of a container have different pressures. The top of the container to the bottom of the container. And what I found amazing was I tried to reverse this pressure gradient using temperature, and that still didn't overcome the electrostatic vector. The gas inside the container was still heaviest on the bottom, even though I had it cooling and the gas on the top was heated up. If that makes any sense. Because heated gas has a higher pressure.
Yeah.
In cool gas, the pressure gets lower and lower and lower until it becomes a liquid.
Yeah, it's because when you heat a gas up, it wants to expand.
Expand, yes. But what happened even in this little container here, I'll show you this one right here. I did this while I was over at Adam McKenzie's house down in Florida, building him a garden. We did all kinds of tests. I was learning how to weld, so we were doing some neat stuff. But I'm going to play this video here. This was from, what's the date? Doesn't say. Oh, February 27th, 2019. So a little over 4 years ago. And here we go.
Hello, everybody out there in YouTube land. Good times for all. There's Zachary Zabala here if you prefer. In this video, we're going to explain what we're doing here. And this is just a very rough start, folks. What we have is a bucket of ice water. Okay? This is a little too warm to be touching right now. This is one of these turned over. It has one of these on the bottom of it upside down in the ice. It is held up. Oh, it's held open right now. So, and that hose is coming out right here, and it runs up to this pressure reading gauge right here, which, as you can see, is right at about 3. And this one is right at about, it's under 2.5, almost a 2. What I've done is I've taken this heating gun up to 800 degrees, and then we have the bucket of ice water at the bottom, and I'm changing the temperature, hopefully, at both ends. So we have the cold at the bottom and the heat at the top. And what we're finding is that we're getting a little bit more pressure on the bottom. Just a hair, possibly. What we really need is another one of these gauges right here. Now, in fact, these gauges may not be 100% accurate. They're old. Some of them are sticky. So this is really just a rough start, folks. This may not actually be doing what it looks like it appears to be doing. So that one's at about 2. We need this one. It appears it's at about 3. So we have, we need better equipment. But I think we can get pressure change from one gradient to another inside a sealed container. There is definitely a huge heat swing that we have here
Okay, we're gonna
on
jump
Earth,
ahead a little
so we
bit.
could then
And
put
we
some
did
threads in
this.
it. So
We did this actually live on Iron Realm Media, and we got the pressure difference to be even more after it sat there for a long while.
tall. But as I open this and let this out,
Oh, hold on.
and it's still at 3, as you can see.
So that one was at 3.
Hard to tell. Show you as that they're connected. Now I'll show you as
That one's
that they're connected.
2 something.
I'll show you right here. I'm going to open this, and it's still at 3, as you can see. Hard to tell.
Okay, open it up.
But as I open this and let this out, this one's going to go down as well.
Yeah, that was just showing that the hose that's running in there is actually connected to the bottom of that cylinder.
So that's at 0.
But yeah, I remember when we were talking about this, Ace McLeod even brought out at a place he was working, they had giant cylinder tanks, and you know, they had different pressure gauges at different elevations to let them know, you know, the pressure at all these different spots on them. So even in an enclosed system, you have a pressure gradient. And that goes against the ideal gas laws. The ideal gas laws say that that's not going to happen, right? And then I've heard they'll say that electrostatics don't affect water the same way it does matter and mass, or mass, or
Water is
solids.
mass, though.
Yeah,
So
yeah,
don't get
solids.
that.
I mean, yeah, no, it doesn't affect water like it does solids. Well, here's a video of
Hello, everybody out there.
me
YouTube
bending
land.
water.
Good times for all here. Zachary Zabala, if you prefer. In this video, I would like to show you, well, I am showing you
The
already,
water's right there. It's bent. You can see the curve.
still bent water.
Now, what I did, this has no charge that I added to it. So this is all charged through induction. So this big sphere down here is the Van de Graaff, the top of the Van de Graaff generator. That puts off a high positive charge, high potential. Then through induction, this is grabbing all the low potential to try to equalize it with this. Well, because it's so close to a high potential, but not touching it through induction, all the low potential is gathering right here on this thing. Because all the low potential wants to get to this high, or yeah, they're attracted to each other, the high and low potential here. All the high potential that's on this sphere will be gathered up here. That's called induction. I have a bunch of other well, not a bunch, a couple other demonstrations on my channel showing how this takes place. Now the water in between is just an insulator, pretty much. It's gonna, now electric field lines are neat because they always touch a surface at 90 degrees perpendicular. So if you have a sphere, all of those, oh, let me turn on this. Now let's grab something right here. So this right here, right? You have this. The field lines from up here are going to come straight off. Straight off. Over here, they're going to come straight off perpendicular. Perpendicular just means 90 degrees. You know, this is your surface, 90 degrees to it. Right here, it would come off 90 degrees, 90 degrees, 90 degrees from that angle. Right here at the edges, you'll even have more potential. The sharper the edges you have, the more potential comes off that. Like, that's why I put the nail at the end of the Van de Graaff generator to make the air flow off of it, to create what is called ionic wind.
Yeah, we
It
see
even
that
has
with
its own name.
we see that with tinfoil and a microwave. It's always on the corners that you see all of the action.
Exactly. That's where most of the potential is trying to escape from the sharper edges. Now, if you have it curved in like this, all your low potential will gather down in that valley, while the high potential tries to get near the peaks. Yeah, that's just how electricity works. And I have demonstrations showing I have a pot with, really sharp curved edges and a really flat surface. And I show you that the charges are different in those different places on the same pot that has the same amount of charge to it. That's just how electricity works. These are the laws of electricity. These are natural laws. This comes from Coulomb, Gauss, Faraday, and Ampere. Those are the four gentlemen that Maxwell took their equations and made Maxwell's equations, which is our laws of electricity and how they work. Now, these are natural laws. These are not like ideal laws. You can test these. You can see it happen in front of you. They're testable. The only reason these aren't scientific is because you cannot remove yourself from the field. You can't remove yourself from this electric field that you're claiming is causing the downward vector.
I don't see how that makes it like.
Well, you have to be able to
disqualifies
manipulate it
from being scientific.
You have to be able to turn it off and on in order to be scientific.
In science, you would have to be able to get outside of the box, or have
you have to be able to manipulate your variable, and then it's physics to me. It's physics. Zetetic,
I just define science differently. Anything that's systematized knowledge in general, that is science.
Always works the same way. Electricity, that's why when you hit the button on your phone, it always turns on, because electricity always works the same way. There is no, except for this one, or we have to make an assumption of this. No, electricity it's scalable. It works the same way, no matter where you are on Earth. Over and over, it's going to function in the same, types of ways. Now, pressure and temperature, all different types of things have effects on electrostatics, and vice versa. When electrostatics discharge, it does this in three different ways: light, heat, and sound. So electrostatics creates all these three different things: light, heat, and sound. Electrostatics can create. And then with heat, you can do all kinds of things. But here, I'll let this video play. I'm sorry, I'm getting off topic a bit. I love electricity.
There's no electric current running anymore.
Oh, real quick. That's why I was saying that, though. But see these field lines right here? They're bending this water because this isn't if this were a flat surface, this would be flat right here still. But because it's bending like this, you can see this arc kind of matches the arc of that ball, because all the low potential is gathering right here, and the high potential in this water is reaching up to try to grab it. So I'm creating a bulge in this still water that's not moving at all.
All the static electricity is in the lid. That is a metal lid right here with rubber around the edges so it doesn't discharge off the edge. We have a discharge ball, kinda metallic spray paint on a ping pong ball on a shish kebab skewer, setting on the Van de Graaff with a tape roll separating it. Now what I've done here is I've charged up the plate to be positive. And then what I did was I discharged the Van de Graaff generator. And so the only static energy is between the plate and the discharge ball up here, the plate and the ball. And what it's doing is it's bending the water. Do you see that? I'm going to discharge it here and I'm going to let it go down. There you go.
Now, did you see that? As soon
That's what it should. Oh, it's still got a little bend to it.
It changed. I didn't have to touch the Van de Graaff generator. I didn't have to touch
bend to it.
The water. All I had to do was touch that
bend to it.
That was holding.
Go down.
Oop.
There you go.
as soon as I did it, did you see
I'm
that
going to discharge
ripple?
it here, and I'm going
It
to let
doesn't
it
go down and touch the water, but
go
look at this
down.
ripple across it. Bloop.
There you go. That's what it should. Oh, it's still got a little bend to it. There we go. But see that now?
Now you notice the
water
background
is
is
flat now.
nice, and it looks just like this back here.
I've
This
been
and
trying to figure
this.
out how I did it for a
It's a
while.
mirror,
I accidentally discharged.
like water usually is.
I'll show you what I did. Charge it up, and it pulls the ball towards it.
Now just charging this up is pulling this ball towards the Van de Graaff generator.
And I could never get it to stay. See how it'll do it, and then it goes away? But now watch this as I discharge the Van de Graaff.
Hope it's starting to right there.
Boom.
And then, now when I did that, there was no more potential down in the Van de Graaff. It's only between this plate right here that's holding the high potential and this ball. That's how I got more of a ripple. You could see it was starting to do it even before I touched it right there.
And then it goes away.
See, it's starting to do it right now.
Discharge the Van de Graaff.
I haven't touched it yet, but you could see the water starting to bulge right through here. You can see the difference in the mirroring. It's starting to fold in on itself. So if I would have been a little more patient, I bet it would have done it without me discharging it.
Boom.
And there you go. Bent water. So electrostatics absolutely affect water.
And you have still curved water. Just like that. It reminds me of the globe, or the azimuthal equidistant map, but the kind with the northern hemisphere.
Had you guys ever seen that one before?
Yep.
I have.
Are you talking about this map, or are you talking about your experiment before?
No, that test that I ran there.
And yeah, that was my first time seeing your test there.
First time with the test.
Oh, sorry. I'm gonna go and I'm gonna grab one more just to show fun with electricity. Oh, where's it? There it is.
The propane.
We will now take. Okay. Oh, it's right here, right at the beginning. Okay, cool. This is on my channel. This is the How the World Works FEIC 2019 presentation videos that Cami and I had put together. So we've been working on this idea for quite a while and we've done many other tests to show this. The downward force, moving matter, different types of matter. Yeah, this one's old. This is where I learned Walter Lewin talking about two plates and why I came to the conclusion it's not just one plate, but two different plates that we have to be in between. But yeah, all these videos are me playing with and talking about electrostatics right here. If you want to see the amount of research and time and just different types of things that I've put into this, go check out this playlist, Fun with Electricity. So I will show this to you real quick.
Take a look at some observations we made to see what we could achieve by creating and manipulating our own electric field and placing different substances between it.
Shout out Alex Michael, Conspiracy Music Guru, for the awesome background music.
In our first test, we simply charge up two metal plates, making one positive and the other negative using a Van de Graaff generator. You can see in the demonstration that by simply switching the positive and negative charges of that which we find here on Earth.
So did you see that right here? The ground is usually our negative when we talk about the Earth and the atmosphere. And the sky is our positive. But what I did was I took the positive from the Van de Graaff and put it down here to this plate. So I'm not manipulating so much the field out here. The field I'm manipulating is between these two plates and pretty much just near the center. Once you get to the edge, you start getting into the fringe lines is what they call it, where the electric field can do some pretty wild stuff and it bends around back in on itself, almost like a toroid. It's really neat. Again, 802, electricity and magnetism. Walter Lewin covers all of this stuff in such depth and detail. That's where I got most of it from, 90% of it, 95% of it probably. But as you can see, our little piece of paper here is stuck to this right up here. I don't know if I moved anything else.
We can get very light objects to rise up from the positive plate below and stick to the negative plate above.
Now, the reason they have to be light objects is because, like I said before, electricity is scalable. So if these plates, which have maybe like 100, 150,000 volts, maybe 200,000, I doubt it's that high with the Van de Graaff generator, just because I get a lot of loss, even though I have it insulated with tape, you get a lot of loss with electrostatics. It's pouring off of this stuff all the time. So it's not going to be the amount that the Van de Graaff is producing here isn't going to get all the way to here and stay in there. So the Earth is over 300,000 volts, which is more than I have on here, but it's also scaled up. So if this plate were 25,000 miles wide, and I had a Van de Graaff generator big enough to charge that up to 100 and something thousand volts, that whole plate, then I could get bigger things to move. But because I have something that's just 1 foot across, the things have to be smaller. But the iron filings I moved were still taller than Mount Everest if you scaled them down to the size of that plate.
Hello, everybody out there in YouTube land.
We'll just...
One thing that's interesting is that this right here literally flies in the face of all the globers who say that, oh, well, it can't be electricity or magnetism because then things that aren't magnetic, it wouldn't be affected. Then how are we moving paper and nail filings? And
everything is magnetic. Everything has dielectricity in it.
Everything is diamagnetic, and along with the diamagnetic, it can also be paramagnetic. In other words, think of diamagnetic as the recessive, everything is diamagnetic and has that property to it. Along with it, it could also be ferromagnetic or paramagnetic, but everything is diamagnetic. Everything. In other words, it's a quality of paramagnetism and ferromagnetism. Everything is diamagnetic. And again, when you're classifying things between diamagnetic, paramagnetic, and ferromagnetic, what you're looking for is the most dominant trait on there that you're going to characterize it. So the most dominant trait on anything iron is ferromagnetic. The ferro is a much stronger mechanism than the dia. The dia is still there, but everything is diamagnetic. And if you have the para or the ferro present also that's more dominant, you're going to name it. It's kind of like having an A blood type if you're an AO and you call it an A because that's the dominant factor in it. And so people are misunderstood about it. Everything is diamagnetic. Everything is, again, these things are through there. What they did was they taught us magnets was only the ferro or the sticky iron action of it. And they separated us, like in science, just saying magnetic is ferromagnetic. It has to do with how things stick to each other as far as metals. And that's not what it is. That's a little sliver of what it is, but it's not what it is.
Well said, Camera Joe. Okay, now here's the scalability thing that I want to show you. I never really even thought about this until I did this. But so the width of Earth, that should be 24,960 instead of 59 I put. So you get 131,208,000 feet. The peak of Everest is just below 30,000 feet. And the peak of Everest would be 0.0002 feet or 0.003 inches. Now, the height of a human hair is 0.003 or 0.004 inches. So Mount Everest would be shorter than the width of a human hair. And 100 miles up would be 0.003 feet or 0.04 inches. So 4/100ths of an inch would be 100 miles up on this scale. So that's just kind of putting it into perspective. So the things that I'm moving around here are taller than Mount Everest. They're bigger than Mount Everest to scale. So these iron, you saw the wood here. I'm going to have to pan the camera up a little, but you see it going up. And I know some of them are still stuck there. 802, electricity and magnetism, Walter Lewin, he explains it all.
Imagine if you looked outside and you saw the city, huge skyscrapers and buildings just lifting up, being ripped out of the ground, and then flying so high up in the sky that you wouldn't be able to see it because their angular size is so freaking small.
Now
That's
that would
just-
happen if we only had one plate. That's
Oh,
why
wow.
I threw away the one plate idea, that we're just on a one plane and,
Doesn't work in reality.
yeah, it doesn't work in reality. Things get induced and they start flying in between the plates back and forth real fast, which would be like that. That would be horrifying. The iron filings, I got some of them to go up. You see some of them doing some pretty interesting little maneuvers in here. Did you see that one? Maybe a shooting star. Watch this. Whoop.
Interesting.
And then human hair. I don't practice on living anything. I refuse. I was thinking about, oh, I could put a flea in there or something really tiny, a small little, but I was like, no, I can't do that. I wouldn't want it to be done to me. So no, I'm not going to do that. But yeah, you can move everything. Everything is affected by electrostatics. That's just how it works. Coronal wind blowing on a candle. I don't know why I wasn't using the big part of my Van de Graaff generator. That was dumb, because this will hold lower potential. There you can see it. This is so horrible. I had to redo all this stuff. But again, that's a plasma. That's not a gas. That is plasma around this. So, I mean, I can blow smoke with it, but the real interesting part is when you put your hand in front of it, you can feel it blowing on your hand. That's how I know. I mean, it's called ionic wind. It's not like I discovered this and I'm trying to promote this. No, this is known for a very long time. Ionic wind. So yeah, I mean, that's pretty much why I came to the conclusion that there has to be, well, I had already believed that there had to be a downward vector of some sort. I wasn't sure how it was created, but I knew that there had to be. What was causing this downward vector, I was not sure.
I want to play Glober for just a moment and ask a question for the panel. And that is that if we do acknowledge that there is a downward vector caused by whatever, right? And that buoyancy, effectively, the thing that's making the gases float is them sitting on top of each other, then can we dismiss the quote necessary antecedent of a container for the gases, for the gas pressure?
No.
No.
Mm-mm.
No,
Has
you have
to
to
be a
create a
container.
pressure. You have to have
Yeah.
you can't have pressure without a container.
But here is a buoyant object. This is a Karen B button.
On my old kitchen floor,
Yep.
yes.
I have it connected to the Van de Graaff generator. It's being floated up by some helium balloons. Now, when I apply a positive charge to it, a higher potential, I'm not changing the density of this object. I'm just changing its electrostatic potential. And when I make it higher, it's going to make this button pull those balloons and go down. Now, I did this. A lot of people said, oh, you're pushing the balloons down with your hand. And this, I did this live at Flattoberfest in front of all kinds of people. numerous times as they kept coming up to the table. So this isn't something that was just done here. I've done this live in front of all kinds of people.
Live in front of a lot of people, and it's something that you can set up and do yourself. And we encourage people to do themselves. Just the same with the ionic wind and such. Feeling of the ionic wind for the first time and reading about it, like on the different tech pages and that, and then actually putting your hand out and feeling it. I didn't know it would be something that you could feel, the pressure differential and that. So again, watching things hit in reality, you learn so much by actually doing more than, again, picking up, more than, again, taking part in this experiment. I wish I could pick up all the nuances that you learn from it. Do you have, Zach, where you show like the different shapes of the electric field, like what would be created with the sphere around,
Yeah.
and showing the energy working in the right hand? Because I know along my learning, and it was an ongoing thing. Keep in mind, I am in this house, and Bob and I worked on it extensively all of the time. It was an ongoing discussion, and we were always looking at different pieces and things missing. And so it was very, very much part of a long ongoing process for me looking at it. And I do know that what really clicked for me, everybody's got different places, where, I had the different pieces of it, but where it all really made sense to me and really clicked in was this, again, the right hand row where no work was required along this axis, and watching how, I don't know if they want to, you guys are explaining it as a pushing, a force, an acceleration, a different thing. And I think, again, the no work required to move along this axis is what made it clear to me, but I don't know what the right word for it is. But I
Now,
think
which
that,
one
again,
was
is,
it, Cammy?
it's where you would show
Oh,
the
yeah.
electric
Okay.
field and the arrow. Again, you have your arrows, your electric field, your different shapes of it, why we know that our plates are flat, because we measure the field this way. And if you're going to take the field with the right hand rule, you'll see that naturally, yeah, I think that's the one right there, Zach. Up to the right, you had your hand on it.
No, that's part 2. This one is part 2.
Right. And that doesn't show the pieces in it? Okay.
Where's part 1? Is it? I can't. Oh, I only have the dearth version. He changed the beginning. Maybe? Yeah. Okay, so it should be right. Coming up.
Because this was huge for me. And again, everybody will have their own little thing. But, and again, where he's talking, this whole thing right here is
Yeah,
very
this
good.
is how I was talking about induction. He's talking about, see, this is a high potential rod. He's bringing close to his surface here. So all the low potential tries to get to the rod, while the high potential, this is polarization.
Polarization and how
through
it works.
induction. And then where is it? There it is.
Yes. Okay.
Oh. Yeah, this was huge for me too. So you have your point charge. Even a very large plane, if it were by itself, would eventually start acting like a point charge. As long as you're close to the surface, they say the electric field will stay pretty much a constant as you rise up. It won't change until it gets so far away that it then starts acting like a point source, and it'll start to convert to falling over at the 1 over r squared, the inverse square law. Then you have, that's a point charge, just one charge. It's positive, so all these are going outwards. It's hard to see, but these are little arrows right here. Then these little circles represent the potential. The closer they are together, the stronger it is. So you have really high potential, and as it goes out, it starts falling off and getting weaker and weaker and weaker. Then you have your electric dipole, which does some really beautiful stuff. It starts making these symmetrical patterns. A lot of they look like owl's eyes if you turn your head to the side.
Right. And it's
Just
the same as your
beautiful.
electric dipole looks the same in electrics as it does in magnetics. Again, your dipole pattern is right there. And if you'll notice, it's touching the center at 90 degrees perpendicular. And this is really important to the surface.
And then, yeah, right here, you have a constant electric field. So you have two different, they call them Gaussian surfaces, however that surface is created. A Gaussian surface, I mean, they say the ionosphere is our Gaussian surface above.
which they
It is
created out of
where our
nothing
high potential comes from, yes. And it's never
because it
been
was needed,
recreated. Yeah, never been recreated in a lab, but
but
it
it has
has to be
to
there.
be there.
That's what they say. This is heliocentric. And that's actually what they say creates our downward vector here on Earth. Like I said, 802, electricity and magnetism. If you want to go straight to that point, it's lecture 2, 40 minutes in. I've shared it so many times with people, I know exactly where it is. Like at 406, he'll start talking about it. But yeah, just go to 42 minutes in or 40 minutes in, and you'll be like right there, 40 minutes, 6 seconds. So and he even says, if not gravity, what holds our world together? He says it point blank. And then he tells you that up to thousands of kilometers, it is electricity that is holding our world together. This is an MIT physics professor teaching students back in the late 90s, early 2000s, something like that.
And when you take this, you take the picture up on the screen he has right now. And if you look at the constant field on it, and let me see if I can put glasses on so I can see which direction the arrows are going. Yeah, there we go. So if you move your positive up, of course, you move your positives up, flip this up so your positives are on top and your negatives are on bottom, and you'll see on here that what it's saying to you is no work is required. Things move along that axis with no work required at all.
And we get this. This is what
And
they
we get
say
this.
our electric field looks like. When you're standing there, you're on the ground, and just above your head, because you are grounded, right, will be 0 volts per meter. Now notice, they don't show the low potential negative lines here on his legs. They start up here near the top of him, because all the low potential will gather up here while the high potential is down here trying to get into the ground. And that's why this bends over him. It's 100 volts per meter right here, but because he's grounded, this is going to bend up over him. So the 100 volts per meter will be up here, and then 200 volts, and then 300 volts. And it's linear. It's not, it doesn't fall off at 1 over r squared like a normal point source does. You have your normal point source here again, and that falls off at the inverse square law right here.
This makes me wonder about like when you lay down to go to sleep, and it's kind of like neutralizing your charge potential, I guess, because you're kind of getting lower to the ground level.
Yeah, that's a good one. Wait, Zach, that barefoot or with rubber shoes on? Yes, that does change things, but you will still have all that potential gathering in the same spots because it is trying to get down there. Like I said, these dances, we can't really see them taking place. We can measure them on things and whatnot, but it's kind of like gases. You can't see it. I would love an electric field viewer that where you could look out and actually see how the electric field is interacting with everything around you. In my opinion, it would look like Neo in the Matrix, how all the edges of everything are a sharper green, and then everything else, like the flat parts, are more blackish. I think that's what the electric field would kind of look like, just like in the Matrix. But no, yeah, once you start bringing insulators like rubber into it and things like that, Bill, it's going to change the potentials, but it's not going to change the overall interaction between you and the ground. So again, I would love to see some people do this. I want to do this. I want one of these. If I get one of these, I will test acceleration to the fullest at different times, different altitudes, different places. I'll go nuts, but I want a digital timer. But this shows in an easy demonstration that the higher you drop something, the faster it is going to fall before it reaches its destination. The potential it has increases over distance.
We didn't even talk about Boyd Bushman, did we?
Nope, not.
And his
nope.
experiment where he takes the two magnets and he forces the north poles together and he forces the south poles together, and they both physically weigh the same amount and they get dropped from the same height, but one falls faster than the other.
Yeah, that's crazy.
That is crazy.
Yeah.
That's a test I've already set up. I just can't find my place to drop them.
Right. It makes perfect sense when you're looking at the whole model, and along with it, it makes sense too about the difference in a thunderstorm. Some of these things start falling into pieces, and little things again start to lay down and make sense because it is dynamic. Again, it's considering all of the sources, but this is there. I mean, this field is there, and in order to do your other things, your ideal gas laws and everything, you have to remove it. In their words, you have to take things outside of reality. I don't think that's our goal. I think we're trying to understand what reality is, and so taking things outside of it, to me, is overcomplicating something and putting. People are saying, "Why aren't you answering, and why aren't you watching the whole stream and coming up with like the answers and watching the whole thing?"
Because things
My
accelerate. Period.
Mhm.
I
and
mean, just do the thought, or go try it yourself. Drop a
Mhm.
pebble from 1 inch, drop the same pebble from 30 inches, and record the splash. The splash will be bigger on the second one. You're going to get more impact. It's going to have more velocity when it hits the surface. That means we are accelerating. If it were the ground that we're accelerating up, the next time you dropped it, it would be even faster.
We shouldn't
I
have to explain this.
don't know how to
It's
explain
simple.
that
Right.
any easier than that. I'm
It's as simple
sorry.
as like climbing a ladder. You know that it's a lot scarier at the top of the ladder than it is at the bottom of the ladder because it's going to hurt a lot more if you jump off the top.
Yes, it's that simple. We are not accelerating up. In order to keep accelerating, it would get faster and faster, and
it would create so
it
many
would fall
problems.
faster and
Yes.
faster and faster every time you dropped it.
You're getting into, to me, you're getting into the realm of a spinning water ball, going around, again, creating things that aren't necessary to fit something when there's no reason for them to be there, because again, with the electric field and that we have in place that we can measure, things would move along that vector and flow downwards with no, again, no work required.
We can go ahead and make fun of Einstein about that all day because that was his whole idea, and he was the big ball earther, and he's claiming that Earth is rising in this direction, therefore, yeah, it should be getting ripped apart, right? According to Einstein's whole theory, and it's just utter stupidity. It doesn't work on the ball, and it doesn't work on a flat Earth either. Okay, that's the whole the Flat Earth Society. That's them claiming that. Oh, that's actually how it works. No, it doesn't. Okay.
Big shout out to Murray Cole over on Rockfin for the $20 super chat. Another great show. Thank you so much, Murray. Much love.
We are not
Cheers,
a floating.
Murray.
We are not a floating space frisbee. Okay.
Oh, okay. So that's pretty much going to do it, folks. Ideal gases, yes, they have their use. Are they real? Do they just hand wave dismiss the electric field? Yes, they do. Are they real? No. If you go into Google right now and ask, are ideal gases real? It will tell you no from 100 different sources. I'm sorry. Ideal gases, they have their place with trying to do math to do things, but when you apply ideal gases, you don't have a pressure gradient. Remember in this part, he said all the pressure in this whole place is equal. Well, we don't see that here in nature. So ideal gas laws are not, explaining how nature works. It's explaining how gas works in this certain condition that can't even be recreated because you cannot remove yourself from an electric field.
Isn't it interesting how they call it a law as well when it can't be demonstrated?
Yeah, they had to throw ideal gas law in front of it. They couldn't just say gas laws because that's like entropy. Entropy is simply high potential will move to low potential, and that's it.
Which goes back to everything is pressure mediation. Yes.
Yes.
Just call something ideal and then make whatever you want, and then
yeah, because you have to make all these assumptions and remove it.
Ideally, it would work like this, right? So.
Yeah, ideally, if you were in space and there was no electric field or anything, and all the atoms were perfect and this and that, and yeah, if you put it in this super ideal circumstances, this is how gas works.
That's when you turn it into a hypothetical.
Yes. And you can't disprove natural laws with this. I'm sorry. it doesn't hold weight for me. Show me, show me this place where the electric field does not exist, this external force, please. So that's my part on it, folks. This is why I have gone to electrostatics.
Yeah.
It's the only.
Uh-oh.
That's not good.
That's now, it may be something else, And now what is causing this high potential and low potential difference? I have no clue. That's like asking what the sun is or what.
Well, I just look at the firmament. There seems to be that difference between the ground level and the firmament.
It's a great freeze frame.
I know. Is that happening to Cammy too, or they're both on the same internet?
I don't know. You there, Cammy? Probably not. Well, it's our show now.
Yeah. I don't know. It seems like it might just end at an impasse for the folks who are on board with the Earth is moving up. But, somebody earlier in the chat said, oh, they're gone. They'll be back in a minute, I guess. But somebody in the chat earlier said, well, the globe moving, or not globe, but Earth moving upwards explodes the globe. Well, I have to disagree with that. First of all, no curvature explodes the globe. And second of all, Einstein already put forth this theory that the Earth was moving upwards. This is not like a new thing. This has been discussed already decades ago, and yet it didn't explode the globe when Einstein purported it. So why would it explode the globe now?
It's getting ripped apart. And so if you have the ground going in one direction in one way and then another way in another way, sorry, then yeah, it's going to get ripped apart, especially if you got up and down as well and just all directions. Yeah, that'd definitely be perpetually exploding, unless you have it all going in one direction, in which case you'd have gravity going upward and then there'd be no gravity going down. And so, yeah, everyone would just be falling off. And that was actually one of the really funny things about Christopher Columbus is when I read, Irvine's book, everyone was afraid of traveling south of the equator because people were afraid of falling off the edge of a globe, which I thought was pretty funny.
Well, the thing that also, when it comes to the downward vector, if it's going to be assumed that it is the Earth moving up, then I just don't know how they reconcile the fact that the downward acceleration is an average and not a constant. It just doesn't. You can't.
Well, that's when somebody in chat said that when you drop something, it gradually loses upward acceleration or upward movement from the Earth. But that
it's a red herring. It doesn't address the point that I made at all, right? That things are falling at actually different rates, and then it just averages to the 9.8.
Yeah.
So, I mean, that wouldn't happen if it was only one thing causing the, one object that was actually the vector, right? And then we're just perceiving it as the reverse, right? We're perceiving everything falling down because it's actually the Earth moving up. Means obviously that the acceleration would be constant. It would be absolute.
Yeah.
I've never to this day yet met any flat earthers who believe that it's actually the Earth that's rising. I've only seen the
This
Flat
is
Earth
a new
Society
development. This is definitely a new development.
The Flat Earth Society is the one perpetuating it, but I've never met any flat earthers who
Well,
actually
apparently
believe
they're
that.
saying Flat Earth Society doesn't say the Earth is moving anymore. I don't know if they changed it because we used to rag on it so bad. Like, to me, it does. I don't even care what Flat Earth Society says anyway. We never really paid any attention to that. We ignored it completely from the beginning. So, I don't really care what they say. But they could have changed their story to try to detract from the real flat earthers more. I don't really know.
That was what Brian Cox quoted. He was quoting the Flat Earth Society with saying that he's like, "Oh yeah, the flat earthers got it right because the Earth is actually rising." And yeah, ridiculousness.
This dude in the chat is like, "Well, that's why mediums come into play." dude, the mediums are on top of the Earth, which is also accelerating upwards. So, I mean, again, it's in the same reference frame, right? It's not like the medium is staying in one place as the Earth and the things are moving through the medium, right? I mean, or is there something that I'm just completely misunderstanding with the argument?
I don't know. I stopped at things aren't accelerating.
I know.
That's when I was like, okay,
And
I
as we
don't
go
need to
into
hear
this,
anymore.
yeah, and in this conversation that we're having, like I'm realizing that I don't think it could really be, you know, can you prove it definitively either way? I mean, we're having the discussion when everybody's stating their points of view, but they keep trying to, you know, well, what about this and what about that? Well, if you guys want to keep going to the what if party, throwing the what if party to try to, you know, keep this conversation going, I mean, I guess you can do that, but I just find it completely pointless at this point in time. I just don't see why we would hang on this one point. Do you?
No. No, Earth's still not a sphere floating through infinite vacuum nonsense. You
And
know,
we're not a floating space frisbee. That's, yeah, a lot of
There's
101.
Yeah, there's a number of things that the globe model requires, none of which can be proven to be true, and all of them destroy the whole model. So I don't even think that we need this. We don't need to even agree on this one point to be cohesively against the heliocentric globe model.
Yeah, we can just agree to disagree. And that's the end of the conversation. I mean, I've explained why I'm not going to change my mind to the Earth is moving upwards, or
Yeah.
electrostatics don't affect gases or liquids or this or that, because I've tested it.
Well, yeah. And to me, in my mind, it's already settled that electrostatics plays a huge part in this realm, and there's numerous other things that you can
Yeah,
see the
buoyancy
effects
and
of it in.
density are still real.
Definitely.
This just sets the direction of the vector.
Buoyancy and density and electrostatics are best buds.
Yep, hand in hand. They go hand in hand together. The
That's
more
right.
dense something is, the more electrostatic potential it can hold on its surface. That's just how it works. It's
Which
very
would make sense why
symbiotic, all of this
liquids,
stuff.
which would make sense why liquids don't separate when you're going in 0G. You know, and like that whole thing about liquid is like the most dense, liquids and solids are the most dense version of any type of material or matter. So when you say that, that kind of makes sense, like why they wouldn't separate when they're currently in motion if they hold on to that charge so much better than something that's less dense. I mean, it just makes sense.
Yeah,
All of it makes sense.
I know that's why I went with it, because it just all fits together. Everything. Even when you talk about pressure, higher pressure systems have more electrostatic potential in them. They have more density. They're holding more electrostatic potential. That's why the high pressure system always goes to the low pressure system. And it's all a dance that this stuff is doing. What Mother Nature is trying to do. And Ken Wheeler always said Mother Nature is this hippie chick with bare feet and bells on her ankles and flowers in her hair, you know, and just trying to make everybody get along and be equal. I used to kind of use that analogy. Now, because if you look to what happens if Mother Nature actually could do that and actually make everything equal, we wouldn't be here. Nothing would. When a little microbe goes and stops consuming other things and creating electrochemical changes to occur in his body, it dies. Entropy takes place and it just dissolves into nothing.
Right.
It has to keep consuming to keep these electrical potential differences cycling things throughout its body and doing all kinds of stuff. Same as us. We have to consume energy. We just have to. We don't, we wither away to nothing and entropy takes place. So, in my opinion, Mother Nature is riding a white horse and carrying a flaming sword. And if she ever gets her way, this place would go back to being of void of nothing, like it was before it all started.
A formless
Makes you
deep.
makes you wonder about the people who feel that nature is just God. And I've had that thought myself, and it's like, well, then how can you also say that God is benevolent when it's obviously so vicious? And then yeah, put your whole perspective on a turntable.
For sure.
Yeah, I mean, I don't know. I don't know. Yep. That's going to be it, though. That's at least my take on how all this stuff works. If you'd like to learn more about electrostatics, please go check out my channel. Just go through some of the neat stuff. You can do all kinds of neat little tricks and stuff with electrostatics. It's fun. And it's amazing how much you can create just by rubbing a couple things together. You don't realize how much power you actually have.
Mm-hmm. Yeah.
It's really neat. It is.
Yeah.
But yeah, and why I don't see the Earth accelerating up, because acceleration means that certain things would take place, and they don't. That's why I don't believe that.
I'm still thinking about benevolence here, and how Karen B would talk about how good means functional, right? Good
Right.
means functional. Okay, benevolence, functional.
So then
That's
entropy
right.
and things just dying would that be unfunctional, or would that be serving its full function because that is the ultimate end state?
No, I think
Uh,
entropy is definitely part of the function. It's definitely part of it.
Yeah.
It's
yes.
crucial.
Mhm.
If there's no entropy, then we would just have remnants of the past laying all around us. We would be buried by the remnants of the past forever. We would
Well, then
never. There'd be no progression or forward motion.
would you be wrong to fight against entropy overall? As in, like, entropy being the thing that ends your existence, right? So would it be necessarily a wrong thing to fight against that? If
I've had
it's
thoughts on this, like about what. Now, I don't think you could do it completely, but the moon seems to do stuff. Um, and the sun does other things. Like the sun brings life and the moon decays, right? And kind of will
That's
turn.
Robotham speaking right there. So.
Yeah, the moon really will. It'll like putrefy things and cause mold to grow on it a lot faster, where the sun will just dry it out and preserve it.
Mm-hmm.
I've heard this, and people have experimented with this. I haven't seen any of the experiments on this yet, but I've definitely heard about them.
Yeah, so I would love to. Yeah, I'd love to. I've only seen some videos and stuff of people like making stuff turn real fast in the moonlight, full moonlight.
But you
Yeah,
also
what if you
have
didn't have to be? What if you could hide from the moon? Would you age as quickly if you were never touched by the moon's,
Good question.
frequencies?
Should you consider that? I guess is the question, right? Because again, if good means functionable, right? Would it be a good thing to do things that avoided the natural conclusion that we're supposed to be faced with, right? Because that's basically it's hiding from the moon, right? To extend your life, basically. Would it be considered functional? Because yay, I get to live and I get to do all these things. Or this is a huge philosophical question that I'm not throwing my 2 cents in. It's actually more suited for the true fate debate. But I was just curious as to the thoughts on that when
The question,
like this get brought up.
I think the answer to your question comes down to: is it functional to be alive in the first place? And yeah, I think there's a kind of a timeliness of it all. Okay, there's a function in being here, and we've got to fulfill that function. And when we have fulfilled that function, there is a time to let it go. And
yeah, it sounds like where you're going is a little bit of transhumanism with that, and again, making it be here forever. Would you want to be?
I don't like resetting the memory card on my video games. So that's just
yeah. I think that's ridiculousness. So.
I had something else, Karen, that you're making me think about.
Hold on 1 second, Kim Joe. Big shout out to Luke R over on Rockfin for the $5 super chat. Good show. I appreciate everything you guys do. Well, thank you so much, Luke. We appreciate it.
Cheers, Luke.
Much
Yeah,
love.
cheers, Luke. And thank you, everybody, for being here and supporting us. And Karen, this is probably something that's occurred to everybody, but it just like hit me the other day. And with what you were saying is, I was watching the digs and they were dating things by how deep it was. So in the globe model, does the ball just keep on getting bigger and bigger? Because if you dig down deeper and the deeper you go, the older it is the ball just growing exponentially? Or how does that work? How did the things, why is the deeper you go, the older it is?
I
Just
don't
a
know. That's
thought.
hilarious, though.
Being
But
so
is the ball
rugged.
getting bigger? That's
Is it getting
funny.
bigger? So yeah, when
It's
you're talking about,
all the space dust and micrometeorites, solar winds.
but that's quite a bit. I mean, if you think about, Barry, you go down 15 feet or 18 feet. Now you take this and make the whole globe bigger, everywhere again. Again, how does that work? But just fun. Oh, let's talk about Oktoberfest. More fun.
Yeah, that's going to be it for that part of the show, folks. I am done commenting on this topic. I've said my piece. I've shown my piece in many, 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 many videos. If you want my take on it, if we disagree, then we just disagree. No big deal. I don't dislike you because we think differently on this.
Word.
I don't dislike globers. I don't dislike my neighbors because they believe in the globe. You know, like I said before on GlobeBusters, it's not important enough to lose friendships and relationships over this stuff. That's the real stuff that matters. Love is what really matters. Whether you have
Yes.
to love somebody that doesn't believe what you believe, but it's not like they're going and doing horrible, evil, wicked things to where it's like, okay, I don't want to be around you, but you butt heads on certain topics. I can still get along with you. We don't have to discuss this stuff and argue with each other. We can discuss other topics and try to advance on those. But we don't have to fight about this stuff. That's silly. We have enough pushback already to be pushing back at each other. Now,
What is this for charity?
healthy debates are great, healthy discussions, but name calling and things like that and all the it
I'm sorry.
I don't want to be a part of it. No, Karen. Not, but yeah, I don't I've said my piece on this. How about you, Karen? We'll just go around the table.
Yeah, I'm with you, Zach. I feel like this has already been settled for me. I just don't really know what else to say about it. It's just I just feel like it, I don't know. It's been settled for me. I like to think about other things and move on to different topics. I just don't feel like it, maybe it needs to be revisited for some people, but I'm with you. I feel like it's settled. It makes sense to me. And then the more observations I make with other things, especially other things I look into like crystals and stuff, it continues to make sense. It really does. Especially
Starts to
with
make
the
more
way,
sense.
right, it makes more sense, especially with the way crystals grow and the properties they have. Like all of this stuff is really interconnected.
Completely.
So yeah, that's it.
I can't believe my ears. I can't believe what I'm hearing, guys. The science is settled. It doesn't need to be talked about again. You guys sound like globers, right?
I wouldn't say it's settled. It's
No, until I
paused.
get like I said,
It's on pause.
It's
this
different.
isn't 100%
Well,
how this works, but
it's a little different because the difference is that when it comes to the whole flat Earth in general, it was a thing that you thought you had looked into, right? You go to school, you get taught the globe Earth model, so you think you have this knowledge of it, but then you actually look into it and you really put the screws to it, and then you find out the truth. Once you've already done that, and then you start doing that to all your other theories, the things that you come up with after probably hold a little bit more weight than things that you held before. But
well,
I
yeah,
do.
when this came to me like the Earth rising, I didn't just hand wave dismiss it and poo poo it. I sat and thought about it a little bit, and I just came up with a bunch of reasons in my head why it didn't work, and then I went and checked those. Now I haven't been able to verify them yet. Once I get that little timer thing, I might be able
Mm.
to. That'll be awesome. But I mean, it's real simple to do it on a cheaper scale, just dropping things from different heights and seeing the impact that it makes, the difference.
And also to the people who are saying, "Oh, we just settle on this. That's how we got the globe." Listen, I can guarantee you that I did not contemplate one single thing about the globe model for 7 long years, the way
Yeah.
that we have done now. I did not put it through the same scrutiny. So to say that is not really a fair statement, because when we were globe believers, we were not questioning things, we were not testing things, we were not scrutinizing what we were being told the way we are now. Yeah.
Yeah. How about you, Kyle? What are your final thoughts?
My final thoughts are that we need to build on common ground. If we want to change minds, we have to build bridges of common ground and invite people to cross those bridges in a friendly manner. But if we're really antagonizing each other, then they're just going to put up these big defensive walls, and good luck trying to persuade them of anything when they've got their walls up.
Yeah. Yeah, you attract a lot more honey or flies with honey than you do vinegar. Well said. And Cammie, did you go?
I think I kind of went before on there. I think we can carry
Okay.
through. I was giving my thoughts on it all. But my biggest thoughts are shout outs to all the people doing the debates lately and what a great job they're doing. Trouble and Tribune. What's it?
Geiler
Mary-
last night. Don't know how you do it, man.
Kyle. Yeah, you guys, people doing the debates.
Patience of saints.
Thank you.
You and Austin have the patience of saints. And
Mhm.
David. I
And
can't
David.
do it. Yeah, I
had
can't
like
do
a
it.
whole I had like a whole nother different way over prepared. I prepared a whole different presentation, and then I realized that there was a problem with it, so I started scrutinizing it, and then I was like, oh crap, this isn't a proof at all. It works out perfectly. So I had to get rid of the whole presentation. I had to do a whole new one, and it ended up being probably one of the best globe debunks and flat Earth evidences ever, because it is. The seeing too far, that's great, right? And even the J. Tolan media, right, when you're getting like 1,000 miles, like that's really good. But when we're dealing with star trail time lapses where we're traveling in a plane and we know the direction of the plane, 3,000 miles of missing curvature,
Mm-hmm.
that's huge. How are you going to get around that? And not only does it debunk the globe, but it also affirms the flatness of the surface. And there's just a way that you can get around this. What's funny about this is that we can invoke geometry. It's a simple, basic geometry for it, right? It does not work for a globe, but it does work for a plane of stars above a flat Earth. So there you go.
Yep. All righty. So, Flattoberfest 2023. It's getting here real quick, folks. August, September, October. It's like less than 3 months away.
Yeah, it's like 70 something days.
I knew you'd be start counting down here.
Wow.
That
Need
is
to look
awesome.
start to look for tickets, Zach.
Yeah, buddy. October 21st and 22nd. Flattoberfest 2023 in Vegas, baby.
The final countdown, right?
It starts from noon to 10 p.m. both days. I love that. I love being able to sleep in a little bit because when you're here, I mean, the presentations have always been great. Every presentation I've seen was maybe not something totally new, but it was really well done, really well put together, and most of them have been something I haven't seen before. Now, but that's not even the funnest part, is the presenters. It's getting to hang out with the presenters afterwards and before, and just hanging out with other like-minded people that you get to see in the chats and things like that, and making new friends, people that don't go on YouTube.
The ultimate backstage party.
It is. It's like the family reunion that you want to go to, because most of the people there are open-minded and have good attitudes. I don't want to jinx it, but has there ever been a fight at a flat Earth One
The
of these
only
big
time there,
gatherings,
the only time
besides when
there,
the trolls come?
yeah, that's just it. The only time is when we get trolls who want to troll the events, and then they come and they try to trigger people. That's the only time that there's ever been an issue. That's not happened at my events. That was one event, one of the FEICs where something like that
Yeah,
happened.
I remember that. Yeah.
But for the most part,
Was
there's
that
nothing
Danny
like that.
Faulkner?
No, he
No, but
wasn't bad. No, it
he
was
showed up, but he wasn't starting any fights.
no.
Oh, okay.
He's a gentleman. Danny Faulkner is. He's
Yeah.
Well, just for the record, you guys are missing out on a huge opportunity to do the Flat v Globe fight night official sanctioned. We have Eddie Bravo on our side. I mean, I think that we do
Bryce
this well.
Mitchell.
yeah. Just line people up. Eddie and Bryce, and just take them all out one
for
after the
charity.
other.
We'll do it for charity.
But yeah, it's going to be awesome time. Mark Devlin from across the pond and Dave Murphy, Jason Lingren, Mark Sargent, Jaron Campanella, Austin Whitsitt, Chief Crow will be playing, Amanda Vollmer, Ben Balderson. Austin's still coming, right?
Yes.
Okay, awesome.
Austin Whitsitt, right?
Yes.
Yes. Austin, and also not on that thumbnail is Greg Reese. We also have Greg Reese from InfoWars. He's like the only guy on InfoWars I like watching.
He's good.
So it's going to be awesome, you guys.
And
It's going to
hosted
be
by the man
fantastic.
himself, Rick Hummer.
Yes.
He hosted all the FEICs. And just a really great guy. I know he looks like a maniac right there, but that's Rick. I mean, he's just hilarious. Yeah.
It's clear he's a maniac.
But that's going to do it for the show, folks. Thank you so much for joining us. I hope that cleared it up for some of you. I saw in chat it didn't clear it up for everyone. I'm sorry, but I don't know how else I can explain my side any more clearly. So I apologize on that. I'll think about it. I'll, and see if I can't come up with some new ways to get this point across a little more clearly.
Maybe respond with a very specific question on what exactly you don't understand about the explanation or the proof, why you feel it's not a good explanation. Let's try to progress the conversation instead of just doing like it does seem like we do with the Globers and just kicking the same conversation back and then having it just be hand waved.
Yes. Well, yeah, and when you
what if we
state
had
things
an
like we're
FE
not,
versus FE debate on modern day debates?
That'd be cool.
That'd be sick.
I
think
not
that
seen
might
one of
be
those yet.
that might be
Someone should bring that up with
their
the guys.
most
Yeah.
viewed debate to date.
Their most viewed debate would be Austin Whitsitt versus Glober Austin. Whitsitt versus Whitsitt himself would probably be their best debate. Say it. He was
Benji
last night.
Benji the Salted with a $10 super chat. Thank you very much, Benji. If I had the money, I would build a casino and make it a map of the flat earth in Vegas. Do you guys have any ideas for rooms and presentations in a flat earth casino? Well, I'd like to show you something, Ben, that I've been working on. Oh, come on, move this whole thing. Oh, it won't let me move it over here. Let me see if I can share it. Stop screen share, present. Here we go. So this is the Fortnite video game right here. And I had to start over, but this is the flat earth map that I'm making. It's 2.5 kilometers by 2.5 kilometers. The last one I did, I had it all the land and everything done, and it was 5 by 5 kilometers, but it took up way too much room. But we have North America, South America, and Greenland so far, and I'm getting better at it. I did all this today, where this before took me like a week.
There's a lot of flat earthers who play Fortnite. Just look for the gamer tag Flat Earth.
Yeah, it's going to be called the Flat Earth Map. So I'm hoping it'll be done within a couple months. The decorating part, I want it to look good. I definitely want it to look good and everything. I don't want to put out a half, But yeah, that's a flat Earth video game. I saw someone mention that earlier about I would love to have a flat Earth video game. Well, it's coming. So hold your
Play Ark.
Hold your horses for
Ark
a
is a
second.
modern video
Yeah,
game.
there you
Fortnite
go.
is a modern video game. Although they do end up showing the flutter as a the floating frisbee kind of a thing, but
Yeah.
but it still shows it a flutter. But yeah.
So yeah, that's gonna do it for the show. GLOBEBUSTERS Tech and the downward vector. I hope that we got our point across clearly. If not, please go check out some of my old videos on my channel. They will answer a lot of your questions on how electrostatics actually work. Or just go watch Walter Lewin. Just type in Walter Lewin, Lewin 8.02, and that will bring up his playlist of all his electricity and magnetism lectures that he gave while he was at MIT. It's amazing. And he doesn't just talk and put up big equations. He actually does a lot of demonstrations. That's why I really fell in love with the way he taught, was his demonstrations. So yeah, that's where I would go to find out more about this downward vector that's created by electrostatics. And if you have any more questions about it, when you see me in chats and stuff, you can ask. But if you're gonna say things like we're not accelerate, things don't accelerate when they fall, and this and that, I apologize for ignoring you. All right, I'm just gonna say it.
You're just denying reality, dude.
Yeah, I guess that's what it is. But yeah, I will be considered denying reality until show me that things don't accelerate. Not by a video dropping something 10 feet with a camera. The demonstration like we showed earlier with, very precise measuring equipment will show this. It's not something you're going to see with your eyes unless you do it from a very dramatic, difference in height. So, okay, I got to stop throwing all these extra caveats in. Show's over. Thank you all so much for being here. Remember, be good to each other. Don't lie to each other. Open your heart, because there's truth inside. Peace out.
Peace, y'all.
Peace.